Alright, so we talked about these UI elements, and next we're going to focus on the specifics of the input matrices and the shader structs. If you haven't already, go ahead and load up Chapter 8, Chapter 8 shader.effects, and also the corresponding max file. Let's scroll down here. We'll stop right here at the automatically tracked tweakables is what we're calling them. These are the matrices that are coming in from the CPU to the shader. Matrices are used in shaders to transform data from one space to another. I could spend the whole DVD talking about how matrix transformations work, but luckily I don't have to because CG Academy already offers another DVD on matrices, and it's a great help in clearly explaining what matrices are and how they work. I highly recommend it. Anyway, so we have four matrices here, and what you'll notice first off is that the data type is float 4 by 4. It's a grid of floats that are 4 across and 4 down. I've given each matrix a name. And these names can really be whatever I want them to be, but in this case I've labeled them specifically so it's really easy to tell which matrix they are. This is the name that I'll use later in my vertex shader when I want to use the matrix. Next we've got a colon. This colon is called a binding. It tells the computer that I want to fill this data type in with a specific piece of data that's coming in from the CPU. So instead of giving these matrices my own values, their values are coming from the CPU. Right after the colon, I've got a specific word that the computer recognizes. Unlike the name of the matrix, this word can't be anything I want. It has to be one of the matrix names in a set that the computer knows. For convenience, I've included a list of matrix names that are available. So these are all the specific words that you can use to bring in specific matrices from 3ds Max into your shader. Finally, we've got a bit of code here at the end that tells Max not to include any UI elements for these matrices. Let's take a quick look down at our vertex shader to see how our world view projection matrix is being used. Here at the bottom of our vertex shader, you'll see that I've got the matrix world view projection, and I've also got the incoming position of the vertex. Now, mul is a built-in function in HLSL, which means multiply. So I'm multiplying the incoming position of the vertex by the worldview projection matrix. And what that multiplication does is it transforms the position of the vertex from object space, which is where it starts, into screen space or clip space. And we take that result and put it into the outgoing position of the vertex. So that's just a quick example of how the worldview projection matrix is used in our vertex shader. And we'll talk about how these other three matrices are used when we talk about more specifically about the vertex shader. All right, let's scroll down a bit here. And next we're going to talk about the input struct. This struct contains all of the vertex data that we're bringing into the shader from the CPU. We'll start off by giving our struct a name, and in this case I've called it A2V, which is short for application to vertex. This struct has 5 members: position, text chord, tangent, binormal, and normal. Just like the matrices, the members of the input struct also have names. So I've given them names, position, text chord, etc. And we use the colon, the binding, and we've bound position to capital position, which is a specific term that the computer recognizes, so it knows to put the vertex object space position into this container. The same applies to the other members of the input struct. Each is bound to a specific piece of incoming data. Here I've provided a reference for you so you know what terms are available for binding. We've got position, text chord 0 through text chord 7, normal, binormal, and tangent. When we talk about the vertex and pixel shader in the next chapter, we'll look at how these structure members are being used in the vertex shader. Lastly, let's talk about the output struct. So we'll scroll down here just a little bit. This struct holds the data that gets passed from the vertex shader to the pixel shader. Just like the input struct, the output struct consists of data type members with bindings and keywords. These keywords act a little differently, though. Instead of telling the computer what data to assign to the variables, these keywords tell the computer which registers to assign the values to. It's as if all the information that passes from the vertex shader to the pixel shader has to fit in one of a limited number of channels to go from vert to pixel. These bindings tell the computer which channel you want each piece of data to ride in. So you'll notice that we have a position register here. The transformed vertex position always goes into this register. Now notice that all the other registers are labeled text chord 0, text chord 1, etc. And we can go up as high as text chord 7. That doesn't mean that we have to put texture coordinates in them, though. It just means that we have 8 slots. Again, I've included a handy reference here so you know which slots are available. We have a position slot, text chord 0 through 7, and also a color slot. We can use these outputs for whatever we want. So notice that we're passing the I vector, the light vector, the normal, the tangent, and binormal in world space using these text chord channels. For the output struct, the data flow is reversed from the input struct. Instead of the data coming, let's scroll back up here so we can see what we're doing. Instead of the data coming from the CPU into the bindings and then going into the elements of our structure, in the output struct, we're filling each of these variables in our vertex shader, and then the data is being passed from here through the binding into the channel, right? And then from there it's going into the rasterizer and the pixel shader. So that covers matrices and the input struct and the output struct. Just for one more example, let me scroll down here to the vertex shader, and you can see again that we've got the position of the vertex in object space, and we're transforming it into screen space, and then the data is going out the position of the output struct. So scrolling back up here, if the CPU is right here, we've got the data coming from the CPU into the bindings and then being assigned specifically to the variables that I've set up. Then these variables are used in the vertex shader. Then when we've got our results that we want, we assign them to these variables in the output struct. And from there, the data flows through the bindings into the channel and then out to the pixel shader. So that's a pretty quick tour of the data flow. And I've gone over the way that the input and output structures fit into how the data is passed around in a shader from the vertex shader, from the CPU into the vertex shader, and into the pixel shader. So in the next chapter, we'll go over the vertex shader and the pixel shader more specifically.